And he's going to talk about spaces of left ordered groups and applications.
Okay. Thank you very much. So, this is the goal of my to talk about the spaces of orders. The reference that we give is a book published, but it's on archive. So it's for groups, orders, and number. So this is available on archive. And if you have any question concerning the text, any remark, actually, there should be still many mistakes in this, many misstrings and so on. So the goal of this lecture also is to finish this book. So any comments you have on this, you're welcome. Okay, so this is what we can go. Orders and dynamics. Okay, so this is my way. And I think Adam already introduced the space of orders. This is very natural stuff. So when you have a group with an order, maybe there is some order which is better than another one than the others, and it is hard to detect a priori an order which is better. And what's natural is to put all the orders in a space, and for the moment, this space will be only a set. So let's say that if you have a left orderable group, let's denote the space of left orders by NO. So this is the set of left orders. Okay, for the moment, this is just a set. And of course, one can do the same thing for a bi-orderable group, for a local indicable, locally, for a group admitting a local invariant order, for a group admitting a coordinate order, and so on. So there are many spaces. Actually, one can consider this even for a group which is not orderable. In that case, this space will be the empty set. Okay? But sometimes it is good to think that way. Okay, even for a group which is not left orderable, you can consider the set of all left orderable on this group. Okay, so this will be the notation. This is for the space of bi-orders. This is going to be very important for us. The space of conradial left orders, also the space of circular orders, and many other. So let me give an example. So I think Adam already discussed this kind of examples. So take gamma equal to Z. This is the simplest example, which is non-trivial. So the space of left orders in this case, this is also the space of bi-orders. This is also the space of radial left orders. And this is just 2 points. This is a set of 2 points. The canonical order and the anti-canonical order. What do I mean by this? Just the fact that 1 is larger than 0. And for the canonical order, the order for which 1 is smaller than 0. Okay, and there are only two ways to put an order on the list. Now, if you pass to some generalizations, well, it depends on what is a generalization. So you can consider C2 as a generalization of C. You can also consider F2 as a generalization of C. And we will see that the situation is very different. Because here, it is a total description of the space of left order. Okay. For the case of the free group, of course, we have to distinguish because a left order can be known by your invariant. So this space is smaller than this one for the case of the free group. And here, the description of the space of left order is not complete. So I will start with recalling with this example. So there are 2 types of orders on C2, and essentially they are like this. Okay. the Cayley graph of C2. So this is the set of lattice points in the plane, and here an order is determined by two. Okay, so the first thing is that you take a line with the origin, and the points that remain on one of the sides will be the positive cone of the order. For instance, this one. This is the positive cone of the order, and this is totally defined in the case that the slope of this line is irrational. But if it is rational, then there are many points, red points in the line, and then you have to choose a direction as well. So it can be this one or this one. Okay, and this is a total description of the set of left orders on the C2. This is an exercise proving that every order on C2 comes this way. So there is a line, and that separates positive and negative element. And in the case of the rational slope, you have to choose a direction on the line and declare that the elements only in one direction are the positive elements.
Sorry, does the lexicographic order also come from this?
Lexicographic orders are of this way because you can take an horizontal line or a vertical line, depends whether you consider the direct or the inverse lexicographic order. You take the horizontal line. I think you have to take the vertical line in order to get the direct lexicographic order. Okay. So you take the vertical line at the ring one, and all elements with a positive first entry will be positive. If the first entry is 0, then you have to choose a direction on the second entry. Okay, and there is a description. You pass from C2 to higher rank, and actually, even in the case of so there is a full description of orders on torsion-free abelian groups. It works like this.
But it generates it all.
Well, let's say finite region. Okay, so Adam told us about some specific classes of groups, or the groups described by Kararin, which are group for which the sum of left orders is finite. This is by definition a Kararin group, and he gave us the full characterization of a group like this. For instance, he proved that if he didn't prove it. He stated that if the set of left orders is finite, then actually the set of left orders on gamma is a power of 2. Constant k. Value not equal number. Okay. This is a kind of generalization of C, because C is the type of, actually this is the only group, the only finite geometric group for which there are only 2 orders. So and an example of this is the Klein bottle group. So this is a group generated by 2 elements. Okay, I will write the relation this way. Okay, one of the elements conjugate the other to the inverse. And for this group, there are only 4 orders, 4 left orders. Okay, and not a very good notation. So for this case, k equals 2. And there is one way to see this. The way that I like to see this is the following. So there is a decomposition of A into 2 semigroups plus the identity. So this is a semigroup generated by positive powers of A and B. This is the semigroup generated by negative powers of A and B. And there is the identity. And there is another decomposition of K as a union of 2 semigroups. So this is the semigroup generated by positive powers of A and negative powers of B. Okay? And this is the semi-group of elements which are products of negative powers of A and positive powers of B. Okay, and it's a nice exercise to check this. So let me give an example for instance. So let's take this element A, B, inverse, A. A priori, this element is not in these semi-groups. But if we use the relation, we can see that we can change this, for instance, because we have this relation. And the relation implies that A inverse equals to B. Okay, if you take the inverse. So we can replace this by B. This is B. A, so this belongs to the semi-group generated by positive powers of A and B. Okay. So every element is in one of every non-trivial element is in one of these semi-groups, and also every non-trivial element is in one of these semi-groups. Okay. And this two decomposition show that there are only 4 orders in the claim bottle group. Okay. This implies that there are only 4 orders on the claim bottle. And the reason is that if I have an order, so there are already 4 left orders. There is a left order for which the set of positive elements is this one. There is a left order for which the set of positive elements is this one. There is another for which the set of positive elements is this one, and another one for the element at this semi-group. And these 4 orders are different. And if you have an order on K, well, you look at A and B, and there are 4 possibilities. There is a possibility that A is larger than the identity and B is larger than the identity. And in this case, all products of positive powers of A and B are positive. So the positive cone of the order is containing in this. So the negative cone of the order is containing this, and so they are equal. So there is no more place in the group. So this case corresponds to the order for which this is the positive cone. There is also the case where A is positive and B is negative. And this case corresponds to the case where the positive cone is, sorry, B is negative. Positive cone should be this one. There is also the case where A is negative and B is positive. And this order should correspond to the order where the positive cone is this one. There is the case where both are negative. Okay. And this, for this order, the positive cone is this semi. Okay. But this is very specific for the case of the claim bottle group. Nevertheless, it turns out that in many cases, orders that appear only for many groups for which satisfy this property. For many Tarari groups, actually this kind of decomposition exists. Yes.
You're not looking at the order up to automorphism. You're not looking at the order up to automorphism.
This is the whole set of orders. So
yeah. But they have an automorphism that sends one to the other.
An automorphism of the Klein bottle.
You mean the conjugacy by A?
Well, if you send P to B inverse,
yeah,
that's
a good point. Yeah. Oh, okay. So I will come back to that. Okay. Okay. Let me say something about it. So in general, so for the moment, this is just a set. But what is important here is that there is a natural action of gamma on this set. So gamma acts on the set of left orders.
Okay. Let's get a quick question about this.
Yes.
Can you Like see directly that if there are finitely many orders, then it has to be a power of two, or do you need to use the fact that there are Carrarian groups?
You really need the full of Carrarian theorem. So there was this description with a rational series, and one can prove that every order is attached to this. The rational series is unique, and every order is obtained by us. By each portion is a rank 1 abelian group. You give a sign to this. So you have 2 to the number of jumps in the rational.
Thanks.
Okay, but this is not very hard, but you have to work to get this. Okay, and this is what Adam mentioned. So there is no similar description for the case of groups, in which the space of biorders is finite. Okay? It's very specific to the set of left orders. Okay, so again, you can find the proof in the God. Hopefully, it's not wrong, but okay. So gamma acts on the space of left order. You can look at the action by conjugacy. So if you take an element F in gamma and you take an order, then you get another order, which is the order obtained by the action of F on gamma on the original one. Okay. Well, how it is defined? Say that G is smaller than H in the new order if and only if the conjugate of G is smaller than than the conjugate of H in the original order. And since we are already working with the order which are invariant in the left multiplication, this is equivalent to that. You can forget about the F in the left. Okay, and you get this. And this is an action. So starting with an order and a group element, you get another. And you can check it.
So on the positive cone, this is just the set conjugation.
Yes. Yes, you take the positive cone and you conjugate the elements in the positive cone by F, you get a new positive cone.
Sure.
Okay. Okay. And your question is a very good one, actually, because we know a lot. We know many things about the space of left orders, but we don't know almost nothing about this space. Okay, and now the key point here.
You say the space, what topology?
No, just the set.
Oh,
At the moment, just a set. Now I will put some topology, and even in the topological framework, well, the situation is the same. So we don't know almost nothing about the question. Okay, so this is the key point. There is a natural topology on the space of orders, and actually it works for any space of orders. You can do the same for left orders, by orders, Conradian orders, although for Conradian orders this is tricky. And well, I learned about this idea from Gis. At that moment, there was a paper by Adam Sikora. But according to Grigorchuk, and I do agree actually, I think that this idea appears for the first time in the literature in the work of Stepping in the 70s. Okay. But anyway, so the idea is very natural. And essentially, I want to define a topology. So I want to define a notion of closeness between two orders. I will say two orders are close over very large, finite. Okay. This is the definition of the topology. And there are two ways of formalizing this. So the first is by explicitly giving the topology. So I will give the elements of the basis of the topology. Okay. There is a topology, there is a basis. Okay. And the basis is take pairs of elements which are different. Finite numbers of pairs of elements, and you consider the set of orders, U, this is going to be an open set for the topology, the set of elements set of orders for which say Fi is larger than Gi. All the orders that make Fi larger than Gi. So this is a set, and you can check it. This is a basis for a topology. And this is a prototype of open set. Okay, so if you have an element, if you have an order for which Fi is larger than Gi, for I from 1 to k, an order which is close to this one is an order for which these k inequalities are still satisfied. Okay.
So this is a basis
This is a,
for the topology.
I think it's a basis, no? It's called a basis.
So it means that the open sets are unions
Yes,
of things like this.
yeah, exactly. This is the basis for a topology. No?
Yeah, no, makes
Okay.
sense. You know, I'm trying to understand. So open means two things are in the same open set. Oh, there is a. Okay.
So an open set is a union of this.
You got a circle for Z squared? For Z squared? You got a circle?
No.
For example,
It's
the
almost a circle.
irrational way. 2 points should give us irrational. Yeah.
Okay, so well, this is the basis for a topology, but actually what I prefer to think is about the neighborhood of an order. You have an order, a neighborhood is a set of orders which that if you prescribe finitely many inequalities, then you satisfy these finitely many inequalities. Okay, this is a typical neighborhood. So let me give an example. Okay, this is boring. 2 points. What is this? And the point now is the following. It cannot be the circle because this space is totally disconnected. Okay. And why it is totally disconnected? Because if you have two orders which are different, well, this means that there is an equality which is satisfied for one and which is not satisfied for the other one. Okay. And this gives you an open set in which the first order is and where the second order is not. So this disconnects the space. Yes.
So these basis elements are all also closed.
Yes. Yes, I think so. Yes, these are properties. Okay. Yeah. And so again, if F is larger than G for one order and F is smaller than G for another order, then you look at the neighborhood, it's at UFG. Well, the first order is in this set, but the second order is not in this set. Okay, so this is an open set that contains this one, but doesn't contain the other.
Sorry, so do you mean?
It's disconnected.
And this doesn't show that this is connected.
It shows that it's housed, or if I
Yeah,
got.
you're right.
Since it's clopen.
Yeah, you're right. You're right. So,
Yeah.
okay. So I will consider.
Say,
I have to consider the other neighborhood.
The other name.
it's disjoint union of the two open set. Yeah, say.
Ah,
Yeah.
Disjoint union of the two.
I see.
So if you have this, then F is different from G. Okay, so the space of left orders. Thank you. It's equal to this union. And the first order is in this open set, and the second order is in this open set. This is a disconnection. Okay. So this space is totally disconnected. What is the nicest space of which is totally disconnected? This is the Cantor set. Okay, and it turns out that the space is the Cantor set, naturally. And the reason is that well, showing that something is a Cantor set, which is something which is totally disconnected, is more or less proving that there is no isolated point. So this means that when you give me an order, and you give me finitely many inequalities for this order, I can construct an order which is different from this one, for which these finitely many inequalities are still satisfied. So if I get an order in C2, remember there was this hyperline description. So if I take the hyperline that describes the first order, and I move it a little bit, then I get a new order which is very close to the original. Except for the case of the rational slope. Because if I move it in the ground direction, then maybe I can kill some positive elements and they become negative. But if I move it in the right direction, they remain positive. Okay. So this is the way of seeing that the space of left orders of C2 is a converse.
So the fact that this totally disconnected is somehow related to the fact that C2 is a discrete group.
No. This is totally general. The fact that
Yeah, I understand that. What if the group I'm trying to order as a topology?
Okay. This is another stuff. So I will not. I will not.
That's-
Yeah. That's a good point. Trying to put some order which respect the topology if the group is already a topological group. So this is something different.
Maybe this is stupid, but the code, like the positive codes, they are subsets of the group, right?
Yes.
What if I consider the Hausdorff distance between these? With this
Okay. This is the
Hausdorff topology. It's like mini.
You are going too fast. Yeah.
Oh, okay. No, I don't know anything.
This is the next question.
Oh, okay. Going forward and breaking things.
So far, this is just a topological space.
Uh-huh.
And actually, the group that I am considering, I put no restriction on the cardinality of the group.
Sure. Yeah.
Okay. Okay. So let me give a fact that it's already a theorem. So the space of left orders of the free group. Well, I say that it's very difficult to describe all left orders of the free group. But in this setting, I can show that this is also a Cantor set. Okay? And this was proved for the first time by Cleary. Very complicated proof, combinatorial proof, and I will give an argument tomorrow. There are many arguments to prove this. I will give a kind of dynamical argument tomorrow to show this. This is also a Cantor set. But actually, these Cantor sets are very different, so I will try to specify this. But this is very interesting. It says that if you take a free group, an order, and finitely many inequalities, then I can win a new order on the free group, which is different, for which these finitely many inequalities are still satisfied.
It's always a compact topology.
This is the next.
Oh.
Okay. Okay, well, this is the key point. So this is LO of gamma is always, independently of the cardinality of the group, a compact topological space. And this is really very nice. And one way to see this, the following. So we have this framework of orders in general. So I will write this. But it's better sometimes to think about, instead of orders, to think about functions defined on. So that would be say -1 + 1 gamma times gamma minus the diagonal. Delta is the diagonal. So delta is the set of diagonals. It's better to think this way. For instance, if you take a left order, this corresponds naturally to a function from this product minus the diagonal to -1 and +1, which says that f phi of fg is +1 if and only if f is larger than g. Okay, and there is a correspondence between orders and functions like this, and the functions that actually define a left order are functions that satisfy some kind of properties. So the properties are that If you change the order, well, you change the relation. So if F is larger than G, then G is smaller than F. Okay. If F is larger than G and G is larger than H, then F is larger than H. So, okay. And the invariance on the left says that the function is invariant on the left. So again, if you have a function from this space to -1 + 1 satisfying these three properties, you get a left order, and vice versa. If you get a left order and if you define this function, this particular function, then you get a function to satisfy this property. Okay, so there is a correspondence. And actually you can change here, you can put by orders, and then you have to add the conjugacy invariance. Okay, and you get again a translation between the framework of orders into the framework of functions defined on this space. And now the point is that the topology that I put here, that I define with these open sets, is the same as the restriction to this space of the product topology. Okay. And the product topology here is a compact topology. The compact space. And these conditions here are closed conditions. So this space is compact. So remember that here, two functions are closed if they coincide infinitely many coordinates. And here is the same. So two orders are closed if they coincide over finitely many elements. Okay. Okay, so this is a standard application of Tikhonov. But what is nice is, again, this is always true, even if the group is not countable. A very large group, the space of orders is compact. This is kind of so exercise. The space of by orders is also compact. Okay. The set of locally invariant orders is also compact. The set of circular orders is also compact. What is not so easy to prove, I mean, if you take the original definition doesn't gives you the result is the fact that the space of conradian left orders is also compact. This is not obvious. Yeah.
Local invariant orders are these not partial orders?
Total orders. Local invariant will mean RRTs. Local invariant. So, but in general, again, if you have some notion of order and you translate into this framework of function from the product, and if the translation gives you a subset of the set of functions which is closed, then you get a compact set. Okay? This is the point. But this is not obvious with the original definition of the conradian property. So let me remind that the definition is that an order is conradian if for every pair of positive elements there exists an n such that fg to the power n is larger than g. Okay? And it is not obvious that this condition passes to the limit. It is not obvious that this condition is a closed condition. Okay? Because there is this n. But what Adam stated yesterday is that one can take n equal to 2. So I can erase this. I can take this. The two properties are equivalent. And now it is obvious that this condition is a closed condition. And now it becomes obvious that the space of conradian left orders is compact. This is one of the reasons why this extension of the property is important. So tomorrow I will concentrate my first talk on the conradian property because this is really very crucial in order to understand the structure of the space of left orders. But now what I wanted to do is maybe I should give a proof of this. That the conradian property is equivalent to the conradian property with n equal to 2. Okay, so the following are equivalent. every pair of positive elements, there is some n such that f g to the power n is larger than g. And the second is that for every pair of positive elements, g to the square is larger than g. This is the good characterization in order to get compactness of the space of Conradian orders. So let me give the proof. So assume this doesn't hold. Okay, then there exists positive f, positive g, such that f g to the square. Actually, it is smaller or equal than g, but I can take a smaller than g. Otherwise, if it is equal, then f would be the inverse of g, but g is positive and f is positive. This is impossible. So the negation of this is this one. Okay. Now we have this. Now I get from this, I get g inverse fg times g is smaller than the identity. Plus I multiply on the left, g inverse. And this element is positive, so this element is, and since this element is negative, well, I have g inverse fg is smaller than the identity, then I multiply on the left by g, I get fg is smaller than g. Now there is the trick. I will consider h as the product of f and g, and I will multiply f by the powers of h. So this is a positive element, and this I can write this way: fg to the power n, which is equal to fg to the power n minus 2 fg. Okay, but because of this, fg is smaller than g. So I can replace this by this, keeping the inequality. So I get this is smaller than fg to the power n minus 2 fg to the square. But now fg to the square is smaller than g. So I can replace this by g, keeping the inequality. So I get this is smaller than fg minus 2 g, which is equal to fg and minus 1 fg g. And again, this is fg to the square, which is smaller than g, and so on. So at the end, I will get that this is smaller or equal than fg g, which is again is smaller than fg, which is fg. So in the end, what I got are two elements, positive element f and h, and f times any positive power of h is smaller than h. So doesn't hold, one doesn't hold. So this implies that this is true. Okay, so this is a very combinatorial proof. So I should say this argument by my student Leslie Jimenez. It's a very nice argument. But tomorrow I will explain what's happening. So there is some dynamics which is arising here, which is encoded in inside. Okay? But this is crucial in order to establish that the space of Conradian orders is compact. So let me now move on the case of say countable groups. Finite originator. If I take a countable group, then I can consider a sequence of subsets. They're all finite, and such that the union of them is the full group. And I can define a distance between two orders. Okay, a natural distance between two orders associated to this inflation of the group is 1/2 to the n, where n is the maximum of n such that these two orders coincide as n. Okay, so when they become different, then you get a positive.
I mean, you have to choose a filtration.
You have to choose a filtration, so. And nevertheless, if your group is finitely generated, it is very natural to take the filtration as being the balls with respect to a finite system of generators. In that case, you have to choose the finite system of generators. Okay. If gamma is a finitely generated group, you choose a finite system of generators, and you can take the SI as being the balls with respect to the system of generators.
So at first step, you have the generators, and then you have the generators multiplied by some other generator,
Exactly.
inverses and so on.
Exactly. Okay. But still, in that case, there is this choice of the system of generators. Nevertheless, there are some properties in the space. Well, I didn't say this metric gives you the topology in the space of record. So the space is metrizable in the case of a countable group.
So, sorry, again. So if the group is finally generated, like if it's the free group, this filtration you would choose is like the words of length less or equal than S.
Yes. And
So did you say you get the same topology independently
yes,
of the
yes.
sets as you choose for any finite sets that exhaust you'll get the same
Yes.
topology?
for the case of a countable group, any of these metrics induces the natural topology.
So they are all equal.
They are all equal.
Okay.
From a metric point of view, of course they are different, but there are some issues that remain. In the case of finitely generated group, if you change the system of generators, then these two metrics are by Lipschitz equivalent. So one can ask, for instance, things like that. So this is an open question. What is the Hausdorff dimension, the space of left orders on the free group? The what? The Hausdorff dimension. So you have a compact metric space, and you would like to compute the Hausdorff dimension. I don't know. So I would like to say it's positive because there are many left orders on the free group. If you do the computation with the case of C2, the Hausdorff dimension is 0. Because you can really count every order. But here it seems to be positive, but I don't know how to. Again, question. What is the structure of the space of left orders up to conjugacy? So this is a topological space with an action. This might be very complicated space.
So sorry if that was asked already, but is the action of gamma on the space of left orders continuous?
Yes, the action is continuous. Yes, it's an action by homeomorphisms.
Why don't you ask it for the whole automorphisms of gamma?
Yeah, of course, you can look at the action of the whole group of automorphisms. And actually, if you take the space of bi-orders of a group, you can quotient by the action of the group of ut of gamma. Okay. You can play the game. But in general, it is very hard to say anything about these quotients. Most of the results concern these spaces, not the quotient. So let me give a question. This is an open question. Does there exist a finitely generated group, left orderable group, gamma, such that the action of gamma on the space of left orders is minimal? It's a very nice question. Minimal means that every orbit for the action is dense. That would mean that somehow all the orders are more or less the same. In the sense that if you take an order and you take finitely many elements, finitely many inequalities for the order, and you take another order, then there is a way to conjugate this order in order to preserve, to respect these finitely many inequalities. So in some sense, all the information of one order contains the information of all other orders.
You understand the action of Z squared on it? space of many orders?
So the action of, so the C squared is abelian, so the action is triggered. So, yeah,
Done.
well, that's.
What about F2, the free group?
Yeah, okay.
So for example, in the case where gamma is Klein inverter group, L is just 4 points.
4 points, yeah. In that case, you can conjugate one order to another one because of your remark, no? And I think there are 2 orbits, maybe there is only one. Two orbits. Yeah, because you cannot conjugate A to its inverse. Okay.
Okay.
There are 2 orbits.
Is this question also open if you change it to another space of orders? So
In general, it is kind of, but let me give an example of a very nice result. Again, this is by Stephen McClary in the 70s. Well, it is not stated like this because at that time the names were very combinatorial, but this is the way I like to see it. On F2, there exists an order, an F order, with a dense orbit. Okay, so there is a way to put an order on F2 such that any other order you put on F2, you take finitely many inequalities, well, these finitely many inequalities are contained in this very particular order. In up to translation, up to multiplication on the right. Okay, so for the case of the free group, this action is not minimal because the free group is bi-orderable. So if you take a bi-order, well, the orbit of this bi-order is just the point. Okay, but there are orders which are not invariant, and there are orders like this, for which the orbit is dense. Okay. So again, so the proof of McClary is very, very combinatorial, but tomorrow I will give an idea how to show this without putting the hands on the order. So there are some ways, some procedures to say, well, there must be some order like this, without saying what is precisely the order. Okay. So let me finish by one remark. So an exotic order on ohmium plus R. Okay, an exotic order. Well, this order is not that exotic because it is a limit of order of natural orders, but it is not a natural order. Okay, it works. Okay, let me give just the construction. So let yn then sequence on the reals, and now take a point on the reals x, and let a sequence xn converge to x. Now I will consider a sequence of natural orders, and I will consider this sequence. So first I will consider x1, y1, y2, etc. This gives you an order in the natural way. So you look at 2 elements, you look at the first entry where they are different, and you declare whether they are. Okay, you have, now you take this sequence and you get another order, and so on. So you take xn, y1, y2, up to, okay? Xn is another sequence that converts to some point x. What we will see is that the explosion at x produces some kind of mysterious. Okay. And now there is the compactness. Okay, this goes up to a subsequent to some order. Well, I claim that this order is not natural, is not a typical order. Again, I cannot put the hands on this order. It is explained just by compactness. Could be some. So claim this limit order is not natural, which means that it doesn't come from a from a sequence of points where you compare two homeomorphisms by looking at the percent where they different. Okay.
I'm a little bit confused. What's the claim that the sequence converges or that there is a subsequence?
No. This, because of the compactness of the space of orders, there is a subsequence of this sequence that converts to some order.
Okay.
And I claim that any limit you get here,
Okay.
no limit can be. Okay.
Sorry, I'm confused about something simpler. How did you define the order from the sequence? I
Okay,
don't
so
understand.
yeah. So if you get a sequence, so the order of the sequence is, for me says that if you take this sequence, so in general, if you take a sequence of numbers in the reals, you look at the first index where they are different, and you declare this. So the first n such that they are different. Okay, this is the definition of a natural order. So whenever you have a dense sequence on the reals, this produces a total order on the model. What I claim is that this order doesn't arise this way, and maybe it's a good exercise. So doesn't arise this way because wow, you prove by contradiction. So this is by here. Okay, I will copy. Okay, so if it arises this way, then to this order there is some sequence which is associated. Say here. Okay. So assume that the first entry of this is not equal to x. If it is equal to x, you have to change a little bit the
Sorry, when you say natural, you mean an order coming from
a
the
sequence.
orange box.
Yes. And then consider consider two elements like this. Take C1, say C1 to the right of X. This is F. And this is the same F here. But now at this point, it is below the diagonal. So F and G coincide on a neighborhood of X. Okay. So here, F is equal to G. But the point is that F of C1 is larger than C1, and this is larger than G of C1. Okay? Because of this property, when you look at the order which is associated to this sequence, you get that F is larger than G. No, sorry. You get that F is larger than the identity and G is smaller than the identity. Okay? Nevertheless, because they are the same here, on the first entry of this order is a point of the sequence, F and G are both positive here. So in the limit, they are both positive. Oh, the orders are the order generated by the sequence is not this one. Okay. A very strange phenomenon. Kind of you look at a point, you somehow you explode the point. You look at the action of the level of gems at this point. In that way, you can make many orders. But again, the key issue here is the compactness of the space of left orders, because I'm just producing something, but not the full order. And the full order is provided by the compactness of the space. Okay, so I will stop here. Thank you.
Well, there is a thing. Maybe I'm slightly okay. Maybe we can discuss. Like, I'm slightly confused by the.
Okay, I have just a small question, namely, you define this topology and it turns out to turn the set into a compact Hausdorff and totally disconnected space.
Also Hausdorff, yes.
So in particular, it's a so-called stone space. And so there's this stone duality for stone spaces that you can characterize a stone space by a Boolean algebra, and if you have the Boolean algebra, you can construct the corresponding stone space. Has anybody tried to find some useful information by looking at this as a Boolean algebra?
No, do you know something? No, no, I maybe this is helpful. We look at the quotient, reaction of gamma. It might be helpful. Yeah. But for the, I don't know of anything in that direction.
So for the group acting on the space of left orders, so in case the group is towering group, so do we know the number of orbits? Is it always 2 or?
Yes,
Yes,
It's always two.
yes.
Yes.
okay, interesting.
Ask Adam.
Towering group orbits?
Always.
Yeah, it's always 2.
Okay.
You sort of work your way up from the bottom, like it's determined entirely by the signs of the generators in each of the quotients. And so you sort of work your way up from the bottom, adjusting the signs to be what they need.
Okay.
And then it's only the top one you can't change.
Yeah, you cannot change the order
Yeah.
of the largest generator, yeah. It's like in the claim, but it works. Because at each level, you have something which is not by order. So there is something which is conjugate to a negative power of it.
Anything else? Yeah, thanks.